All right, let's do one more example here. If you're following it in the book, it's example 13.3. An automobile tire spilled to a gauge pressure of 200 kilopascals at 10 degrees Celsius. After driving 100 kilometers, temperature in the tires rises to 40 degrees Celsius. It is the pressure in the tires now. Okay. Now, the reason I want to use this example is when we use the ideal gas laws, we need to be dealing with absolute pressures, not gauge pressures. Okay, so you need to go back to your fluid section. Remember back there what a gauge pressure was. It's the absolute pressure minus the atmospheric pressure. Basically, if we're looking at a tire here with the valve stem, it's the difference between here and here. Okay. So we have the absolute pressure and we have the atmospheric pressure. Our gauge pressure is the difference between the two. So if you put a gauge on here, it's going to tell you the difference. Okay. So first thing we need to do is find out what that absolute pressure is. Okay. Well, our gauge pressure here is the 200 kilopascals. So kilo means 1,000. So 200,000 newtons per meter squared equals our absolute pressure minus 1 atmosphere. Okay, well, I count the zeros here. 1, 2, 3, 4, 5. So this is 2 times 10 to the 5th newtons per meter squared. So that being the case, I can just subtract this or add this to here. What we get is 301,300 newtons per meter squared equals our absolute pressure. Okay, now remember that we've got to use the temperature in Kelvin. We've got 2 temperatures here. Temperature 1 is 10 degrees Celsius, so add 273, that's 283 Kelvin. Temperature 2 is 40 degrees Celsius. Add 273, that's 313 Kelvin. Okay? Now, if we look at our ideal gas equation, PV equals nRT, okay, we're dealing with pressure, volume, and temperature. Okay, so let's get all the things that change on one side of this equation. PV over T equals nR. This is just going to be a constant. N times R is going to be a constant. We're not changing the amount of air in the tire. Okay, and R is just a constant. Okay, so that part stays the same no matter what else changes. So our first pressure, volumes, and temperatures here are going to be equal to our second pressure and volume and temperature over here. Okay? These give us the same constant. So our equation here that we're going to be dealing with is P1 V1 over T1 equals P2 V2 over T2. Okay. But we've got something else that doesn't change here. It's our tire. It has the same volume. If it has the same volume, V1 equals V2. Those cancel out. So, pressure 1 is right here. T1, 283 Kelvin, equals pressure 2, which we're trying to find, divided by 313 Kelvin. When we solve for P2, then what we get is 3.32 or 332 times 10 to the 5th newtons per meter squared. Okay, so here's our absolute pressure. Again, if we want to find our gauge pressure, so our gauge pressure then is going to be 2.319 times 10 to the 5th newtons per meter squared. If I round that to the three significant digits, 2.32, and then put it in kilopascals. So 232 kilopascals. So it went from 200 kilopascals, sorry about that, to 232. Now I said we were gonna, there were two forms of the ideal gas law. We're gonna look at the other form right now. Here, we're giving the ideal gas law in terms of number of molecules instead of number of moles. Okay, so our number of molecules is going to be our number of moles times Avogadro's number. So capital N is number of molecules, M is number of moles, and Na is Avogadro's number. Okay, and this should make sense because it goes back to the definition of what is a mole. Well, a mole is Avogadro's number of atoms. Okay, so if I have 1 mole, then the number of molecules I have is N1 times Avogadro's number. I've got Avogadro's number of molecules. Okay, if you don't remember Avogadro's number is 6.02 times 10 to the 23rd, and it's either molecules or atoms per mole, depending on whether we're dealing with an element or a molecule. Okay, well, if that's the case, then our ideal gas law equation, PV equals nRT, now becomes PV equals divided by Na, the number of molecules, by Avogadro's number, and what we do is we take this right here, since it is always the same value, and we give it a new name or new value of K. So this is PV equals capital N K T. Okay, and this is the other form of the ideal gas law. This is the ideal gas law in terms of number of molecules. This is the ideal gas law in terms of number of moles. Okay. Our value of K then is just going to be one of our values of R. In this case, we're going to use the divided by Avogadro's number. We're going to use our 8.315 joules per mole Kelvin divided by Avogadro's number. That gives us 1.38 times 10 to the 23rd joules per Kelvin. They call this Boltzmann's constant. All right, let's do a couple of examples here. This will be a hydrogen atom mass. We want to use Avogadro's number. to determine the mass of a hydrogen atom. Well, our mass is just our atomic mass, since we're dealing with an atom instead of a molecule, divided by Avogadro's number. Okay, so when we look up in the periodic table, the mass for hydrogen, what we get is 1.008 grams per mole.